So pause and copy all this. Pause and copy. So we are going to find a volume in a different way, and we'll see that we come up with a technique that is very different and very useful. So what are the ingredients? We got 1 over x here, and we got a boundary below the x-axis and the vertical lines x equals 1, x equals 3. So we're taking this region R, which is this region I'm shading right now, and we're going to rotate it about the y-axis. So hopefully you can see kind of a volcano looking solid. So our technique this time is to take this rectangle like usual, but we're going to rotate it about an axis that is parallel to the rectangle. You see the axis we're rotating about and the rectangle are parallel. So we're going to do that rotation, and what do we get? Well, we get what's called a cylindrical shell. Okay, it's a cylinder, and it's pretty thin. Okay, there's only a little delta x worth of thickness there. So pause and copy that figure if you haven't had a chance to already. So we're going to be basing our volume integral on this object here. So we'll need to find the volume of just this one cylindrical shell. So how do we do that? Well, what we're going to do is we're going to imagine we have a pair of scissors and we just cut this guy right about there. And then we unroll it. And what do we get? Well, roughly speaking, we get this kind of rectangular looking solid with a little bit of thickness delta x. Of course, this delta x down here is the same as this delta x right here. Okay, now that we have a rectangular solid, we can very easily find its volume. We're just going to go, base times height times depth. Now you'll remember that f of x is the function we're talking about. So I've copied here the original picture. So remember, we've taken this rectangle, we have rotated it around the y-axis, and we obtained a cylindrical shell, which we cut and unfolded to get this rectangle guy up here. So the height in red here is the same as the height in red here. Okay, so how do we find the volume of this rectangle thing? Let's go with a nicer color, blue. So we'll say volume of this, we'll call that delta V. So a chunk of volume, a piece of volume. Well, as I said, it's base, which is 2 pi r, times the height, times delta x. Now I've forgotten to explain where the 2 pi r comes from. Where the 2 pi r come from? Well, let's scroll back up and have a look-see. What is this 2 pi r? Well, if I go back to the cylindrical shell, it is the circumference of this circle up here. And what is the circumference of a circle? Circumference is, well, 2 pi r. Okay, where r is the radius of the circle. Okay, where were we? Trying to find the volume of this rectangular thing. And we did 2 pi r f of x delta x. Okay, so just base times height times depth. Okay, so what we'll do is the same thing we did in the previous technique, is we imagine this region here being filled with rectangles. So you got rectangles all through this region. Okay, you fill it in a reasonable way. And then you find the volume of the solid obtained from each rectangle. And then you're going to add them all up, right? Oops. So this is going to give me, when I add up all the cylindrical shells, look at this guy. And, of course, fudging a bit, the actual volume I'm looking for will be represented by an integral. 2 pi r f of x dx. And we are summing from 1 to 3. And that's the 1 and the 3 down here. Okay, so in our case, what do we have? We have the radius. Let's talk about the radius. On my diagram down here, the radius is, well, I'm going to look at this rectangle here. And the radius, I'm going to extend a vertical up here. The radius is the distance between, the horizontal distance between this rectangle and the axis of rotation. So here's my r here. Now what's that? Well, it's so easy, it's hard. This r is exactly just x. Okay. Okay, you can see here I've labeled the point at the top of the rectangle, x, f of x. So my radius is just going to be x. So I'll plug that into my integral. Get 2 pi x. And the function we'll remember is 1 over x. And in this case, we get a nice integral that simplifies very nicely. We get just 2 pi surviving here, 2 pi dx. 2 pi is a constant, so we get just 2 pi times x as the antiderivative from 1 to 3. So we get 2 pi times 3 minus 2 pi times 1. So that is 6 pi minus 2 pi, 4 pi. Okay, exercise for you. This one's a very optional one. I want you to try this. Do this with washers if you can. It's okay to give up, because the point is that trying to do this with washers is going to be difficult, or at least awkward. So, but if you don't believe me, then try it.